Okay. Our next job from here, now that we have our exact time in GMT, is we need to find the GHA, the Greenwich hour angle of the sun at each of these exact times. Remember, one of our ultimate goals is to find the LHA, the local hour angle of our shot. But before we can find that, we need the GHA, which is equivalent to the longitude of the sun at the time. However, to get there, you need to remember that the Nautical Almanac writes out its GHAs in hourly values and then has a separate correction seconds section to find the minutes and second values. So we're going to have to break that down before we can eventually find it. So how we're going to write this out is our next section. We're going to write GHA hours, which is the hours, the hours value of the GHA. And then we're going to write minutes and seconds. And then we're going to write GHA. That's how we prepare the worksheet. Oh, one second. I left the Nautical Almanac on the couch. And now that we have that ready, we're actually going to come to the almanac and we're going to open it to the page related to our day we're working with, which in this problem is the 18th of August. So we open it up. Here you see we have the 30th of June, the 1st of September, July. I have to just flip through a lot of pages. 11. Okay, August 17th to August 18th, meaning this is the 17th, the 18th, the 19th. So this is the day we're working with. You have to remember though, this page is mostly for stars and planets. You have to flip to the other side of the page to get the sun. So all of this column is the information we need, and we're working with specifically this section here. So here you can see on the left of this column, we have the GHA, the hourly GHA, and then on the right, we have the declination. So we're only interested in the left here for right now. Now, we need the GHA of 1700 on the 18th. So we're going to come to the 18th, the sun column. We follow the GHA down until we reach 1700, right there. Okay, so at 1700, the sun had a Greenwich hour angle, so equivalent to a longitude of 074 degrees, 04.0 minutes. So that's what we're going to write here. 074 degrees, what did I say? 04.0 minutes. That's how far away from the prime meridian it is right then. At 1700, not at 1736, 12 seconds. So now what we need to do is we need to find how much that changes in an additional 36 degrees, or 36 minutes, 12 seconds. So for that, instead of working in these daily pages, we have to flip all the way to the back of the book to the increments and corrections pages, all the way, also called the minutes and seconds pages. And we're going to come to the 36 minutes column. Here, 36 minutes. And then we're going to follow it down to 12 seconds. So as you can see, the way these columns are set up is this whole box is dedicated to 36 minutes. This whole box is dedicated to 37. This one to 32, this one to 33, and then the pages continue on this side too. On this half of the box though, this is all declination and things related to declination. So we don't need to worry about that just yet. This is all GHAs. And then we have GHAs for the sun and planets, for Aries, and for the moon. So right now, we only need this column. So we're at the 36 box, and we're looking for 12 seconds. So we follow it down There's 12 right there. We come across, and 36 minutes and 12 seconds of movement of the sun is equivalent to a change in arc of 9 degrees and 3.0 minutes. So now we come here and we write out 9 degrees, 3.0 minutes. So it went an additional 9 degrees and 3 minutes in its direction since 1700 at that time. Now, you never need to ask yourself, oh, do I add or do I subtract? Because when it comes to GHA and minutes and seconds, you always add. Because GHA is always going to the west, so it's always increasing. Unless you wrap around from 359 back to 000, you're always adding your values as you rotate around the Earth. So we just need to add this. So we add the two together, we get 7 minutes. And then we get 74 plus 9 is 0.83 degrees. So, while the GHA of the sun at 1700 was 74.4, at 1736 and 12 minutes exactly, the GHA of the sun was 83 degrees and 7 minutes on the 18th of August. Good. Now we're going to go to the next one. Here. We're going to set up the same process. So we do GHA hours, then minutes plus seconds, then GHA. Okay. This is happening on the 4th of June. So step number 1, we come over here and we go back to the daily pages. Oh, I jumped straight to June, so that helps. So then we come through June 6th, 7th, and 8th. So here should be 3rd, 4th, and 5th. Perfect. So now we're on this set of 3 days. Here's the 4th. Now we are looking for June 4th at also 1700 because these two problems happen to be really similar. So we come here. We see at June 4th, on June 4th at 1700, we have a GHA of 75 degrees, 26.1. So I'll write that out. 0.75 degrees, 26.1 minutes. Now that's really similar to the previous problem because at 5 p.m. GMT one day versus 5 p.m. GMT another day, some other time during the year, it's not unreasonable for those two times to have similar GHAs. You know, the fluctuation happens, but it's relatively minor. So it's not crazy to think that they're both around 75. You know, 5 hours from the prime meridian is also 75 degrees west. So they're the same things, just one is thought of in terms of time and one is thought of in terms of distance. Now we need the minutes and seconds. So in this case, we had minutes of 15 minutes and 20 seconds. So we head back to increments and seconds, or increments and corrections. There we go. We head over to 15, 16. We turn the page. And then this side. Here's 14 minutes and 15 minutes. And now we're going to follow the column down for the 15 box till we get to 20 seconds. We've got 3 degrees and 50 minutes. So anytime the sun moves for 15 minutes, it is moved 3 degrees and 50 minutes of arc. So we write 003, 50.0 minutes. And now, as always, you only add, you never subtract. So we do 26.1 plus 50. We got 76, so we subtract 60. 16.1. We carry the 1, so that's now 76 plus 3. We get 79. So this problem has an exact GHA, a longitude of the sun, of 79 degrees, 16.1 minutes. Finally, now we go to the next problem, and we're going to do it one more time just for practice. we do, these numbers are just good to separate the different types of values you're working with. So like this is all hours local, this is all hours off of the chronometer, this is GMT, and now we're working with GHA. I always want to break them up so I don't just get lost in the sea of numbers. I actually know what I'm looking at the whole time. So we've got GHA hours, minutes plus seconds, and then GHA. Step 1, we find the GHA hours. So we have to come to the day, 21st of November. Here we've got September, October, a little bit further, 24th of November, 21st of November, and it's the 1st, the 2nd, the 21st, 22nd, and the 23rd. So here we've got the 21st. We come over to the sun side of things. We've got the 21st. We're now looking for 0300 Greenwich Mean Time. So we come to 21 in the GHA section. Here's 3. 228 degrees, 32.9 minutes. 228 degrees, 32.9 minutes. So we're now dealing with a different GHA time. So it's naturally the GHA itself, the difference in arc between the prime meridian and the sun is going to be different than the 1700s we've been working with before. So this is the value at 0300 on this day. Now we come to the minutes and seconds, or the increments and corrections. Right here, we're looking for minutes of 16. So here's the 16 page. And seconds of 3 seconds. So there's 3 seconds. We get 4 degrees and 0.8 minutes of arc. So we write 0.04 degrees, 0.8 minutes. Then we add them together. 32.9 plus 0.8 is 33.7 minutes. And then 228 plus 4 is 232 degrees. So there's our GHA at the exact time 03/16/03 GMT on the day of the 21st of November, specifically 1981. And now we've finished the GHA section of all of our problems.